I want to talk about kind of a small goal. I want to talk about the universe, but particularly the two great pillars of our understanding of the universe that we've built over the last century. And we're still building absolutely now two of those pillars that I hope you're going to contribute to building in the future. The two pillars, two things that maybe you don't learn about at school, but you'll certainly learn about at university. One pillar is called relativity, which is Einstein's great contribution to science. And the other one is something called quantum mechanics, which is a fascinating theory. It seems very strange. You may have heard of things like Schrodinger's cat. Things can be in two places at once. But actually, quantum mechanics is our theory of everything that happens in the universe other than gravity. And today, the place where we explore that in detail is the Large Hadron Collider at CERN in Geneva, the place that I work when I'm not messing around on television. So I want to give you some idea of what we're doing now at the Large Hadron Collider and what we hope to discover within the next year or two. So absolutely current cutting-edge research. But the first thing, I think, to say about the ambition, because I said we want to understand the universe and our two great theories of it, is to look at the sheer size of the problem. And that's one of the things that I think captured my imagination first when I first began to get into science, when I was 5, 6, 7 years old. It was the sheer ambition of it. Because this is a picture of the universe. This is actually a picture of the night sky. If any of you are interested in astronomy, that thing up there is the constellation of Orion that you can always see in the winter sky. But I want to I want you to focus on a piece of sky that's somewhere around here. I'm going to zoom in on it now. It's a piece of sky that you would cover if you took a 5p piece and held it about 25 metres away. So imagine taking a 5p piece and putting it 25 metres away over a tiny piece of sky. Well, a few years ago now, the Hubble Space Telescope, which is in orbit around the Earth, turned its gaze to that tiny piece of sky, the 5p piece bit of sky, and took a picture. It opened its camera shutter for thousands and thousands and thousands of seconds and just gathered the light from that piece of sky. It was deliberately chosen because it's a dull, uninteresting piece of sky. Actually, from the surface of the Earth, you would see virtually nothing in it at all. But this is the picture that Hubble took. And you see that it's anything but empty. It's called the Hubble Deep Field image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty. It's got lots of structure, lots of points of light in. There are actually over 10,000 points of light or blobs in that image. And virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now, those galaxies on average have, 100,000 million stars like our sun in them, at least. So 100,000 million stars in each one of those 10,000 blobs. The most distant object in that image, and I'm going to talk a bit about how we know these things in a moment, but the most distant object is 13.2 thousand million light years away. It was actually discovered in this image only a few months ago. Now, light travels at 300,000 kilometers per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to the Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began its journey to Earth before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. So imagine what that looks like. That's a tiny, remember, 5p piece of sky 25 meters away. Imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Every dot on that map is a galaxy, with 100 billion stars like our sun in it, at least. You see that the structure in there, they're not randomly distributed. It's very interesting. I'm going to show right at the end of the talk that we think we're beginning to understand where that structure came from. Just to get some sense of scale, that little line up there, you might not even be able to see it at the back, but that's the 1 billion light year line. So light takes 1 billion years to travel from one end of that line to the other. This is the observable universe. And I'm going to show you, there's a ridiculous number that I have to show you. It's better to show it than say it. This is the number of stars that we think are in the we know from observation are in the observable universe at the moment. 30,000 million stars. Just like our sun, some bigger, some smaller. 350 billion large galaxies, 7,000 billion smaller dwarf galaxies. That's the observable bit of the universe. We have pretty strong evidence now the universe is significantly bigger than that, but we can just see this blob surrounding us, the blob from which light has had chance to travel during the history of the universe. So the universe is big, is what I wanted to say to you. I don't know if you know a comedian called Woody Allen. He once said that the universe is probably infinite, which is a bad thing if you're one of those people who can't remember where they put things. But it's enormous. So how can you... Oh, I don't want to start that yet. There we are. So how can we possibly begin to think about explaining that? You know, how do we know, first of all? How do we know it's so big? How did we find that out from this planet that we're standing on now? And how could we begin to make theories, guesses, I suppose, if you like, about where that came from, how it began, how fast light travels, all those facts that I've said to you, or all those numbers that I've given out that are our best estimate of how the universe works. It is, of course, science. And I wanted to just play you a little video of, for me, what the best definition of science, or the scientific method that I've heard, comes from a very famous physicist called Richard Feynman, who won a Nobel Prize for building one of the first quantum theories of electricity and magnetism. It's called quantum electrodynamics. This is back in the 1940s and 50s. It's our best theory today of how light interacts with matter. But Feynman was also, I recommend that you read his books. He was a brilliant teacher, a brilliant lecturer, as well as a Nobel Prize-winning physicist. And he gave this lecture back in, I think it was the 1960s, and it's just a 1-minute definition of the scientific method.
I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we... No, don't laugh. That's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
So I think that's a really beautiful description of what science is. It's really very simple. It's the application of common sense in many ways. What it is looking at the universe, looking at nature, guessing about how it works, seeing what the consequences of that guess are, testing those against nature, and as Feynman said, the great power of science. It doesn't matter who you are. There's no such thing as authority in science. If your guess disagrees with nature, then it's wrong, and that's all there is to it. Easy to say, but how can we possibly compare ideas about the origin and evolution of the universe with nature? Well, if you think about it, there's only one way to look into the wider universe from Earth, certainly the universe beyond our solar system, and that's to gather the light from distant stars and planets. And there is an immense amount of information contained within that light. This is our sun. It's a tremendous, I think, video of the sun. This is not a computer graphic. It's a real movie of the sun taken by an orbiting spacecraft that just observes the sun every day. And you see that it's a dynamic and violent place. You could fit 1 million Earths inside that ball of glowing plasma, by the way, 1 million planet Earths. It burns 600 million tons of hydrogen fuel every second into helium. So it's a powerful, gigantic object. Many years ago now, stretching back to Newton and even before, we looked at the light from the sun, and after Newton, we found a way of analysing it by splitting it up into its component colours. So with a prism, essentially making a rainbow of the light from the sun, just as nature makes a rainbow of sunlight using water droplets. And this is a picture, a modern-day picture of that rainbow. Now, rainbows, of course, lots of different colours from blue all the way to red, but when you look at the light from the sun in a laboratory and you're very careful and you put it through a very precise prism, then you see that it's not just an array of colours, it has dark lines in it. All these black lines crisscrossing the rainbow. What those lines are the signatures, the thumbprints, if you want, of the chemical elements themselves. See, what happens is you'll know that an element is a nucleus with electrons going around it. And each element has a different nucleus and a different arrangement of electrons. What happens with the light from stars is that the light shines through elements in the star's atmosphere. So elements like hydrogen and oxygen and helium. And because those elements have different structures of electrons around their nucleus, they absorb different colours of light, very specific colours that correspond to moving the electrons around in very specific ways. So, for example, these two lines here are very famous. They're called the sodium lines. Sodium absorbs light in the yellow part of the spectrum. If you heat sodium up, it emits light in the yellow part of the spectrum. Why? Because of the way its electrons are arranged around the atom. So what you're seeing here is the signature, the fingerprints of elements in the sun. That's interesting in itself because you can immediately read off what the sun's made of, because you can do an experiment on Earth, see which colours the elements absorb or emit, and you can look in the starlight. You can see what the stars are made of. But also, and this is the point for looking at the wider universe, something very interesting happens when you look at these spectrum, these black lines in the rainbows of the most distant stars and galaxies. So here's a distant galaxy. You can look at the light from that galaxy. What you find, of course, is that the spectrum is the same. The black lines are all the same because chemical elements are the same across the universe, except that in all distant galaxies, the lines are shifted. They're moved. They're not in exactly the same place. Now, one explanation for that, of course, could be that the elements are somehow different in different parts of the universe. But it's interesting, isn't it, that they're all shifted in the same way. And actually, there turns out to be a pattern to this shift. So what's the explanation? Well, the explanation for the shift is very simple. The universe is expanding. So if you look at a very distant galaxy, then you find all the distant galaxies are rushing away from us. Think about what that does to the light. What happens to the light is the light begins its journey from the distant galaxy. Light is a wave. You just imagine a wave on its journey through space. The space is stretching because the universe is expanding as the light journeys from the distant galaxies to us. What does that do? Well, it stretches the light. So the wavelength of the light is stretched. The wavelength is the colour. Red light has got a bigger wavelength than blue light. So as the light, let's say it comes from a star, it's a hydrogen, let's say, emits a line up here, and that journeys across the universe to us, it gets, actually, let's start in the blue. So let's say there's an element down here that emits light in blue. It journeys across the universe, it stretches, it stretches, it stretches. It moves towards the red bit of the spectrum because it gets stretched. And so you see the whole fingerprint of the atoms moved from the blue bit of the spectrum to the red as the light gets stretched, as space stretches. That's what we observe. So that's a very direct measurement that tells us that the universe is expanding. That's one piece of the puzzle. So just qualitatively, you can say that tells us our universe is stretching. Space itself is stretching.